So let's say we move our object. When the object is far from the mirror, our two rays intersect at the place that would be the top of the candle. The bottom of the candle stays on the principal axis just like it would for a lens. And so I see that our image is inverted and smaller. Now, bringing this candle closer to the center of curvature, we see that that candle image is getting larger, but still real, still inverted, still smaller, until right on top of the center of curvature. This up and down arrow right now is because it's going from the top of the candle through the center of curvature. Imagine it's hitting a big spherical mirror that encloses the entire surface. So then it would go hit the mirror surface and then reflect backwards. This gives an image that's roughly the same size, but inverted and real. And as we get closer to the focal point, notice that the image is now magnified. It is larger than the original object. Larger, 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 larger. But what happens when I have the candle, my object, on top of the focal point? When that's true, how about we go right here? Now notice the black and red rays are completely parallel to each other. And since they never meet up either on the real side of the mirror, that's here, the left, or the virtual side of the mirror, that's on the right, there is no image formed when the object is on top of the focal point. Bringing the object closer, you can see the red and black rays are intersecting somewhere off screen, over here in the back. And let's just bring it down so we can see a little bit better. This is forming a larger virtual image. And the closer I bring it to the mirror surface, the smaller that image becomes, but it still has a positive magnification. It's still larger, a positive larger than 1 magnification, still larger than the original object. And if I go closer to the focal point, that image is larger. Notice that this has all the same characteristics as converging, convex lenses. When you're far, you get an inverted smaller reel. When you're on the center of curvature, you get an inverted same size reel. When you're between center of curvature and the focal point, you have inverted larger reel. No image because parallel lines. And then finally, if you bring this really, really close, this is your makeup mirror scenario. Imagine you put your face really close to a makeup mirror. You see a virtual, upright, larger version of yourself because you really wanted to see all of your pores up close. Now let's deal with a convex mirror. Think of one like a silvered surface of a sphere. Imagine I have like a big silver ball here. Remember, center of curvature is always in the center of your sphere. So in this case, the center of curvature, and therefore the focal point, are on the other side, the opposite side, the virtual side, from your real object. But notice that our patterns for ray 1 and ray 2 are the same. Ray 1 starts from the top of the object, goes to the center of curvature, and because, notice right here, this meets the mirror perpendicularly, the light hits the mirror and bounces back, right? So this black ray right here would extend back out over here. Our eye in this scenario is over on this side, perceiving the black and red diverging rays of light. The red ray does the same behavior as ray 2 in the concave case. It goes parallel to the principal axis, but then it diverges away from this focal point instead of converges towards. Since the light diverges, it has to obey the law of reflection. So it goes towards the mirror, reflects parallel to this normal line, and is reflecting away from the focal point. So our brain, with our eye on this side right here, we're imagining us right there, sees the red and black rays of light. And because those rays are diverging and our brain assumes light travels in a straight line, we perceive a virtual, smaller, upright image. And no matter where I put the candle, it's always virtual, smaller, and upright. This would be used for things like your side view mirror. The reason a side view mirror is good is because, like a fisheye lens, it allows for a larger field of vision by making all the objects in the mirror appear smaller. Now, if you ever noticed on the side of the mirror. So let's see if we can figure out exactly which rays need to be drawn in order to use ray diagrams as a method to determine images. So first off, let's say I have a converging mirror. And just like converging lenses, rays that leave the top of the object and travel parallel to the principal axis should reflect back towards the focal point, something like this. I'm going to call this ray 1, and I'm going to leave it in blue. Ray 1 should leave the top of your object, travel parallel to the principal axis, and then out through the focal point. And if you need to pause this to draw this video, by all means, do that. Ray 1 is going to look exactly the same for a diverging mirror, with one small exception. Okay? As that ray goes parallel towards this mirror, remember that this is a diverging mirror, so it needs to reflect away from the focal point. So, something like this. Ta-da! The ray goes parallel in and away from the focal point. And I'm using a dotted line back here to denote that this dotted line is not real light. The real actual ray has traveled away from the surface of the mirror and doesn't exist back here where, the wall would be if this were a plane mirror. So ray 1 either goes parallel in and towards the focal point, or parallel in and away from the focal point, depending on whether it's a converging or diverging device. Ray number 2. This ray is going to leave the top of your object, and instead of traveling through the vertex like it did in the lens, this is going to travel through the center of curvature. And I want to point this out here. As it leaves the object, goes through the center of curvature and hits the mirror, what angle does it form between the ray and the surface of the mirror? I'll give you a second to think about it. That should be a right angle. Now I'm going to draw ray 2 in red. Since that's hitting at a right angle, a ray that leaves the top of the object and goes through the center of curvature will hit the mirror at a right angle and bounce exactly backward from which it came, which I will draw in red, represents light that's traveled from the top of the object through the center of curvature, reflected off the surface of the mirror, and bounced straight back. And if you're keeping track of this, these two rays are enough to determine the top of the flower. So my flower is definitely going to be inverted because the top of the flower has to appear where those two rays intersect. And since the stem of the flower has to come out of the principal axis, there is my image. Smaller, real, and inverted. Number 2 again is going to go from the top of the object through the center of curvature. But please note here that this never actually makes it to the center of curvature. There's a mirror in the way. So it's probably better to say ray number 2 leaves the top of the object, hits the mirror, and then is reflected straight back along the path from which it came. Something like this. From the top of the flower, as if it would hit the center of curvature, and back out the way it came. Ta-da! And our brain, seeing these two diverging rays of light, thinks to itself, self, those must have come from the same location back behind the surface of the mirror, and so our brain sees a smaller, virtual, upright flower whose top occurs at the intersection of those two rays. So, at this point, you should note that ray 1, the blue ray, goes parallel in and towards the focal point. either towards the focal point for converging or away from the focal point for diverging. Ray number 2 goes from the top of the object through the center of curvature, hits perpendicular to the mirror, and so it bounces straight back. Goes towards the center of curvature, hits perpendicular, and bounces straight back. Now, if you really want to, there is a third ray for these, and I'll draw this one in. But since 2 rays suffice in order to find the location of the image, for this, I'm going to draw them and show you what they look like, but don't feel like you need to be able to draw these perfectly on your own. The third way that we can draw here would leave the top of the object and then go directly through the focal point and come out parallel. But notice that ray 3 has the same location as the intersection of ray 1 and ray 2, so it is redundant in terms of finding the image. Similarly, ray number 3 would leave the top of the object, go towards the focal point, and reflect out parallel. But since ray 3 hits in the same location as ray 1 and ray 2, it's redundant in terms of finding the properties of the image. So, for the last section for homework then, let's review and practice getting our interpretations using ray diagrams for concave and convex mirrors. When we come back tomorrow, we'll work on mathematical substitutions as well as looking more at being able to predict what sort of reflections are made for converging and diverging mirrors.